So in order to do calculations based on chemical reactions, those reactions must be balanced. Okay, and we know how to balance chemical reaction. Think of it this way. If you were going to bake a cake, but you had to bake 2 cakes, you would have to have the recipe, number of eggs, the number of cups of flour, etc., etc. So it's the same thing with chemical reactions. So why do we want to do calculations based on chemical reactions? Well, let's say I've got A reacts with B to produce product C, and I want to know how much A is required to react with some specific amount of B. Let's say I have a specific amount of B, and I want to know how much A do I need to go get in order to completely react with all of the B that I have. I could also ask if a specific amount of A is provided, given that I had an unlimited amount of B, and that would be my assumption, how much product C could I make? And then I could also ask if I needed a specific amount of C, how much of reactant A would I need to go get off the shelf if I had an unlimited amount of B? Maybe B comes out of the atmosphere. Maybe it's oxygen. Okay, and I'm trying to make a specific amount of C. Okay, let's take a look at a balanced chemical reaction. I've represented it in 2 different ways. This is the way we normally see a balanced chemical reaction. I just wanted to make sure that you understood exactly what we were representing here. That's all this representation is. 1 mole of dinitrogen, 3 moles of dihydrogen, just H2, and then 2 moles of NH3. This is nitrogen, and each of the yellows, those are hydrogens all the way around those 2 molecules. All right, so here's how we work this kind of calculation. We need to relate the number of moles we have of one reactant to the number of moles we need of the other reactant, or alternatively to the number of moles of product that we want or we're going to produce. All right, and we do that through a device that we call the mole to mole ratio. You may recognize this is put together in dimensional analysis format. We have an X factor. And here's what this problem says. Given that you have 3 moles of hydrogen, how many moles of nitrogen are required to completely use up all 3 moles of hydrogen? And notice that we aren't concerned in this particular problem with ammonia, NH3, only with nitrogen and hydrogen. All right, so here's the deal. The X factor winds up being the numerator in what we call the mole to mole ratio. And we get the mole to mole ratio from the coefficients from the balanced chemical reaction. If there's no coefficient, it's understood to be 1. The coefficient of hydrogen in this case is 3. So the coefficient of the X factor goes in the numerator of the mole to mole ratio. So now when we multiply across, moles of hydrogen will cancel, we'll wind up with moles of nitrogen, and we get an answer of 1 mole of nitrogen. So let's work this problem again. Let's just step it up a little bit. We're going to double the amount of hydrogen that we need to consume. Our X factor is still moles of nitrogen, so it's still the numerator in the in the mole to mole ratio, which is just the coefficients from the balanced chemical reaction. All right, and so we do the math. Moles of hydrogen cancel, and we wind up with moles of nitrogen, and it's just going to be 2 moles of nitrogen. All right, we can also use this technique to figure out how much product we can produce. So in this particular case, here's the deal. I've got 8 moles of hydrogen. Now, nitrogen isn't mentioned, so we're making an assumption about nitrogen. it exists in excess or an unlimited amount. Maybe I'm getting it from the atmosphere. So I do not need to worry about reactants that exist in excess, only reactants that have some limited amount. And so I have a limited amount of hydrogen here. My X factor is moles of ammonia, so I know that's going to be the numerator in my mole-to-mole ratio. Okay, mole-to-mole ratio. And so my coefficient of ammonia is 2. It's in the numerator of my mole-to-mole ratio. Moles of hydrogen will cancel, and 8 times 2 divided by 3, and I'll get 5.333 moles of ammonia that I can produce if I have 8 moles of hydrogen and an excess or unlimited amount of nitrogen. Let's do one more of these. In this particular case, I'm not concerned with the ammonia, with my product. What I'm saying is I have 12.7 moles of nitrogen, and I need to know how many moles of hydrogen will be required to completely use up or consume all of that nitrogen. My X factor is hydrogen, so it's going to be the numerator in my mole-to-mole ratio. And so I wind up with moles of nitrogen canceling. I wind up with moles of hydrogen, which is 38.1 moles of hydrogen that I'm going to need to completely consume 12.7 moles of nitrogen. Okay, so that's how we work those problems. The format is going to be pretty much the same for all of the problems that we'll do, but let's make it a little bit more complicated. So unit conversion for these calculations has to go through moles. You can do it with mass ratios. It's trust me, you don't want to. You would much rather go through moles. So in every single case, if we're given grams, we're going to convert it to moles. How do you convert grams to moles? You know this from empirical formula determination. You divide by the molar mass. So here we go. In order to use a balanced chemical equation to calculate the amount of product or reactants, we have to convert grams to moles. We have to convert grams to moles. We have to convert grams to moles. And finally, you may have to convert moles back to grams. So we're going to work on several of those problems. All right. So here's a famous reaction. This is the reaction that is used in space vehicles to consume the buildup of carbon dioxide from the exhalation of human beings. And this is called a CO2 scrubber. We use lithium hydroxide. Now, the first thing you have to remember is that your reaction must be balanced. And this one is not balanced yet. You've got 1 lithium and 2 lithiums over here on the product side. So we need to go ahead and balance this reaction, and now we're balanced, okay? All right, so the question is, how many moles of lithium hydroxide would be required to produce 2 moles of lithium carbonate? That's what this compound is. This, how many moles is our X factor. So our X factor is X moles of lithium hydroxide. That's always the how many, how much, etc. So X moles of lithium hydroxide. And what goes on the other side of the equal sign? The other stuff. And the other stuff in this case is 2 moles of lithium carbonate. So we're going to put 2 moles of lithium carbonate. Now, my X factor is lithium hydroxide, so when I put together my mole-to-mole ratio, all I have to do is go up, see the coefficient of lithium hydroxide. It's in moles, so that's going to be 2 moles of lithium hydroxide. The other stuff, the coefficient of the lithium carbonate, is understood to be 1, so it'll be 1 mole of lithium carbonate. And then I do the math. The lithium carbonate's going to cancel. 2 times 2 divided by 1 gives me 4 moles of lithium hydroxide. Okay? That will be required to produce lithium carbonate. Notice that CO2 is not a factor in this. It's considered to have more than I could possibly need, an unlimited or excess amount. In this particular case, the how many moles of carbon dioxide is the X factor, so that's going to be X moles of CO2 equal to what I need to completely react with 8 moles of lithium hydroxide. That's the other stuff, so that goes right here, 8 moles of lithium hydroxide. Notice that we're not concerned about water. We're not concerned about the lithium carbonate. My X factor is moles of CO2. My coefficient for CO2 is understood to be 1. So it'll be 1 mole of CO2 and then 2 moles of lithium hydroxide down here. Why do I have to have 2 in the denominator? Because my coefficient of lithium hydroxide is 2. When I do the math, moles of lithium hydroxide canceled. I get 8 times 1 divided by 2 gives me 4 moles of CO2. And that is how much CO2 would be required to completely consume 8 moles of lithium hydroxide. And it's a 2-to-1 ratio, so that makes perfect sense. All right, so this one's a little bit more difficult. Why? Because we're given 18 grams of CO2 and the X factor is how many grams of lithium hydroxide. So that's our X factor. So this is a more complicated problem because we're given grams and we're asked for grams. And they all work the same way. So this is going to be how many grams of lithium hydroxide equals 18.0 grams of CO2. Okay? Now the first thing I have to do is I have to convert grams to moles. All right, that's step 1. How do I do that? I divide by the molar mass. 12.01 for carbon plus 2 times 16 gives me a molar mass of 44.01 grams for every 1 mole of CO2. All right, so that gets me out of grams of CO2. The next step is the mole to mole ratio from the balanced chemical reaction. This is going to be moles of CO2 here, and this is going to be moles of my X factor, because remember, the X factor is what goes in the numerator, and I go up here and I remind myself that the coefficient is 2 for lithium hydroxide, my X factor, and the coefficient for CO2 is 1. And so when I multiply and divide across, moles of CO2 will cancel. So step 2 is the mole to mole ratio. And then finally, I need to go from moles of lithium hydroxide to grams of lithium hydroxide. All right, and every 1 mole of lithium hydroxide, and you know what? I don't know the molar mass of lithium hydroxide. Let's go ahead and calculate it. Lithium has a molar mass of 6.94, oxygen a molar mass of 16, and hydrogen a molar mass of 1.01 grams per mole. So lithium is 6.94 grams per mole, oxygen is 16, and hydrogen is 1.01. That gives me 23.95 grams per 1 mole of lithium hydroxide. And when I multiply and divide across, moles of lithium cancel, and I wind up with my X factor, which is grams of lithium hydroxide. Let's see what we get. So how many sig figs are we going to have? Well, we started with 3. Okay, that's 3 sig figs. And we don't have to worry about the molar masses because we've got 4 sig figs for all those. So that's going to be 18 divided by 44.01 times 2 divided by 1 times 23.95. And that gives us 19.59 grams, but we can only have 3 sig figs, so our actual answer will be 19.6 grams of lithium hydroxide. Okay, so let's just take a look at everything we've done here. We went from moles to grams. So we have grams to moles, mole to mole ratio, and then moles to grams. How do you convert grams to moles? Divide by the molar mass. Then you have the mole to mole ratio, which are just the coefficients from the balanced chemical reaction. Your X factor, which in this case is lithium hydroxide, is 2. I don't know where my 2 went, but there it is 2. So that's why we have a 2 here. Coefficient of carbon dioxide is 1, and then we multiply by the molar mass to convert moles to grams. So moles to grams multiplied by the molar mass. Moles to grams multiplied by the molar mass. Grams to moles divide by the molar mass. And then the coefficients from the balanced chemical reaction are where the mole to mole ratio comes from. There's my 2. All right, so let's work this little problem. For the following reaction, calcium plus 2 moles of water make calcium hydroxide and hydrogen gas. And it's asking how many moles of H2 are formed from the reaction of 6 moles of H2O. Here's the deal. You're given moles and you're asked for moles. Your X factor is moles. And you are given moles of water. So there's no need to convert grams to moles. You don't need Avogadro's number. It's just a one-step conversion using the mole to mole ratio. We'll just check and see if this is balanced. I've got 1 calcium, 2 times 2 is 4 hydrogens. I have 2 times 1 is 2 hydrogens plus 2. 2 times 1 is 2 oxygens. 2 times 1 is 2 oxygens. So I'm balanced. I've obeyed the law of conservation of mass, so the rest is simple. How many moles of H2? And equals, and we have 6 moles of water. And now our mole to mole ratio, and moles of H2 go in the numerator because it's our X factor. Moles of water in the denominator. So let's just go find our coefficients. For water, the coefficient is 2. For hydrogen, the coefficient is understood to be 1. So this is 6 times 1 and divided by 2 moles of water, so that's going to cancel. So that gives us 3 moles of H2 that'll be produced from 6 moles of water and an excess amount of calcium. So don't get fooled by this kind of problem, which just gives you moles and asks for moles. It's a one-step calculation. I think this is the last problem we'll do in this video. Let's go ahead and see how this works. All right. So first things first, is this reaction balanced? Yes, it is. Okay. Calcium carbide, this compound right here, reacts with water to produce acetylene. This compound right here, just so you know what it looks like, you've got a triple bond between the carbons, and that's acetylene. And that's just an aside. You don't really need to worry about that. Production of 26 grams of this. So you've got 26 grams of this stuff over here requires the consumption of X grams of water. So there's your X factor right there. So this is X grams. So this is going to be a gram to gram conversion. So you're going to have to convert grams to moles. You need a mole to mole ratio, and then you have to convert moles back to grams. So my X factor is X grams of H2O equal sign. What goes on the other side? The 26 grams of the other stuff, which is the acetylene, C2H2. The first step in this problem is to convert grams to moles. How do I do that? I divide by the molar mass. So this is going to be 2 times 12.01 plus 2 times 1.01. And that gives me 26.04 grams for every 1 mole of C2H2. When I multiply and divide across the 26 grams of C2H2 cancels, and I wind up with moles. Next, this is the mole to mole ratio. Okay? And let's take a look at that. We've got moles of C2H2 in the denominator and moles of H2O in the numerator. Let's go up and find our coefficients. Coefficient of water is 2. The coefficient of C2H2 is understood to be 1. That's a little crooked, but it's a 1. So that's 1. When I multiply and divide, moles of C2H2 cancels, and I wind up with moles of H2O. Last step, I need to go from moles of H2O to grams of H2O. Now, I will tell you this. Water is going to, we do most of our chemistry in this course in water. You need the molar mass of water, and rather than have to figure it out each time, it's really handy if you just know it, because it's so easy, and we've worked with it before. It's 2 times 1.01 plus 16, and that is just 18.02 grams per 1 mole for water. That's the molar mass of water. When I multiply across and divide, moles of water cancel, and I wind up with grams of water. That's my X factor. So let's see what we've got. So we've got 26 times 1 divided by 26.04 times 2 divided by 1 times 18.02, which gives us 35.98 grams of H2O. Is that my final answer? No, because when I look at what I started with, I only had 2 significant figures here, so my answer has to be 36 grams of H2O. I can only report my answer to 2 significant figures. And by the way, this last step was moles to grams. So let me just go through that. This is called a gram to gram stoichiometry problem. So in a gram to gram stoichiometry problem, you convert grams to moles by dividing by the molar mass. You have the mole to mole ratio. Just remember, whatever your X factor is, That coefficient goes in the numerator, mole to mole ratio, and then finally moles to grams, and you multiply by the molar mass and make sure that you report your answer to the correct number of significant figures. All right.